Hello, everybody. Can you hear me okay? Yeah. Just in case you think you're in a different place, this is not the precise training that was originally scheduled. It was flipped precise or swapped. That was run earlier. So this is about solids for foam. So it's a broadly related topic, but I won't feel offended if you want to leave if you thought this was about precise. Okay. Let me introduce myself. My name is Philip Cardiff. I'm an associate professor in University College Dublin in Ireland. And I've been working on this toolbox with others for the last few years called Solids for Foam. And this is what this training is going to be about. Yeah, if anyone online has questions, I guess you can just put them in the chat, or if there's any problems, you can put them in the chat. Yeah, just to get this out of the way, I'm not affiliated with OpenCFD and I acknowledge OpenCFD. So, solids for foam, what is it? Why does it exist? And how is it designed or implemented? So what first? So solids for foam is an OpenFOAM toolbox for computational solid dynamics or mechanics and fluid-solid interactions. So it aims to just build on top of the OpenFOAM base libraries and just add solvers or a solver specific for solid mechanics and fluid-solid interactions. This is one of many ways that people can approach FSI in OpenFOAM. So for example, everybody's familiar with the dam break example, but you could extend that to do a flexible dam break problem, which is also seen in literature. So on the flexible dam break problem, your little dam now is a flexible object. In this case, it's an elastic object, so it doesn't dissipate energy. And then as the dam breaks, the pressure and viscous forces cause the solid to deform, and the mesh moves as well. So that's different. You need to have a dynamic meshing procedure as well for your fluid and ALE procedures. But it's not just for FSI. Solids for foam, a subset of FSI is just S, which is solid. So you can do stress analysis and solid mechanics in it as well. So this is a metal forming problem crushing an aluminium pipe. Last year, I gave a training as well. We were in Cambridge. So this is Isaac Newton, in case you didn't recognize him. So this is just a bust of Isaac Newton wobbling, made out of rubber, because why not? And one thing which has changed since last year is there's now a Solids for Foam website, a landing page. So you can go to solids4foam.github.io, and there's some basic documentation and some tutorials, like some of the tutorials I'm going to go through now are there, and it gives instructions on how to install Solids for Foam, etc. as well. And it links to the GitHub page also. Just a note, previously, Solids for Foam was hosted on Bitbucket, but now we've moved to GitHub. Some of the reasons for that were to do with build minutes. You essentially have unlimited build minutes with GitHub, but on Bitbucket, you have to pay if you want to have over a certain minimal amount. Also, GitHub Actions, you can set up a lot of automation, and there's maybe a larger community than in Bitbucket, even though you can probably do the same thing with Bitbucket as well. But there's a lot of public GitHub Actions that make that easy to do. I am going to move to some hands-on terminal, but I'll just have some content to go through before that. So just a brief history. If you in college did stress analysis, it was probably linked with a finite element course. So in fact, FEA is a synonym for stress analysis. Typically, when people will say FEA and CFD, where FEA is meant to be stress analysis and CFD could be any numerical method, but that's not a very good name. So just computation solid mechanics can use one of any number of numerical methods, just like CFD can. So since the late 1980s, there were papers exploring finite volume methods for solid mechanics, a variety of different approaches, just like we see in CFD. There's these Demirdzech type approaches, which are similar to what we have in OpenFOAM, but there was also, let's say, kind of fast, explicit, compressible type approaches, and also vertex-centered approaches and staggered grid approaches. In fact, Stephen Beale, I'm not sure if he's at the workshop, but he's definitely part of the OpenFOAM community. So he had an early paper in this area. If you happen to go to the Wayback Machine, you can find nabla.co.uk. So Nabla, if you don't know, is the company that initially tried to commercialize foam before it became OpenFOAM, with Hervé Jacek and Henry Weller. That didn't work out, but you can find their webpage. And as a service, they advertise stress analysis in OpenFOAM at the time using some of these early methods. Subsequently, then a variety of different people worked on OpenFOAM specific solid mechanics developments. And then there's things like the solid mechanics toolbox, Extend Bazaar, Foam FSI, and then there are many other independent toolboxes as well. And then solids4foam came about in 2016, essentially just generalizing the Extend Bazaar approach. Why does it exist? This may be clear, but just to make it explicit, there's a desire to solve FSI interactions, or fluid-solid interactions in OpenFOAM. Probably this is why many of you are here. There's also a desire to run solid mechanics cases natively in OpenFOAM. Also, another one is, which is interesting given recent directions of the foundation, particularly the new version was released today, so it's apt, this modular approach. So originally, when you wanted to do FSI in the OpenFOAM style approach, if you wanted one type of fluid solver like pimple foam and another type of solid solver, you had to just copy and paste them into the same solver. So if you wanted to change something, you had to make a new solver. So having a modular fluid and a modular solid means that at runtime, you can select which ones you want to use. So I'll talk a little bit about that. And then just one thing for me as well, I'm interested in finding volume methods, and particularly for solid mechanics and FSI, and exploring new numerical methods. So it's essentially a toolbox that just lets me and others do that. The other way. So that's what, why, how is solids4foam implemented. So the kind of ethos or the approach is if you can use OpenFOAM, you can use solids4foam. So it's just an OpenFOAM case. It's just an OpenFOAM solver. So the physics maybe are different, which you have to understand, but that's essentially it. There's an aim to support the main forks of OpenFOAM. That doesn't mean every version, but at least the main forks. And it should be relatively easy to install. And I tried to force an emphasis on code design and style as well. So just to mention on the single executable design, which is not the OpenFOAM approach. Actually, before that, just to comment on supporting the different OpenFOAM forks. And by OpenFOAM forks, if you don't know what I mean, there's 3 main versions of OpenFOAM. OpenFOAM.org, known as the foundation version, OpenFOAM.com, known as the ESI version or OpenCFD version, and then there's Foam Extend. They're very similar. 95% of the code is probably similar, but they're painfully different in that 5%. So the way that's supported in solids4foam is using compiler directives. Essentially, you'll see in the code in places, it'll say if def OpenFOAM ESI or foundation, then this is how you get access to the reference for a temp field, whereas in Foam Extend, it's using the old version. They never updated it. So this is how that's supported. Then to comment on the single executable design. So solids4foam is just one solver. It's not like OpenFOAM. It's not a series of solvers. It's just one solver. And that solver is just a shell. And it calls a module called physics model. So that's just a base abstract class, which has some interface defined. And deriving from that, we have solid models, fluid models, and FSI interfaces. So for example, in a fluid model, it could be pimple fluid or interfluid. And just by the naming convention, you can see pimple fluid is basically just a class version of pimple foam. Interfluid is a class version of interfoam. So in that way, solids4foam, the solver could act exactly like pimple foam if you just choose at runtime a fluid model called pimple fluid as the physics model. Then it'll act just like pimple fluid. Just like there's many approaches to solving fluids problems in terms of different assumptions about the physics, like incompressibility or compressibility, but also different numerical algorithms and discretization. So you could have finite volume, finite element, cell-centered, vertex-centered, explicit, implicit, coupled, etc. You can do the same thing for solid solvers. So there's a variety of different solid solver approaches. And then if you choose an FSI problem, then it will create a runtime selectable solid model and a fluid model. And then you can select what each of those does. And then you have some extra things to choose, like how you're going to couple them, what coupling scheme. Just to comment on the single executable design, just checking on Twitter today, OpenFOAM.org released OpenFOAM-11 today. So I'm pretty sure they always do it during the OpenFOAM workshop. I'm sure it's by coincidence. So if you had been tracking OpenFOAM -10, the development version, they've been deleting solvers. So they're refactoring the entire solver structure into a modular structure. So I'm sure not inspired by solids4foam in any way. It just happens to be similar. And so they'll just have one solver and you'll have modules that you can pick, like pimple fluid, except they're not called pimple fluid, et cetera, et cetera. So they haven't explicitly targeted FSI, but certainly it's designed to be able to do FSI and conjugate heat transfer, things like that. So I think it's a good thing. There seems to be people who don't think it's a good thing on Twitter, and I understand their perspectives. So yeah, it's definitely interesting. So what's new in solids4foam 2.0? The main difference, which made it go to 2.0, is that it breaks backward compatibility. So it supports newer versions of the different OpenFOAM forks. So OpenFOAM v2.0, 9 and foam extend 4.1 are supported. Whereas if you use v1.0, it's an older version. So just changing the v, the first digit, implies breaking backwards compatibility. So anytime the first digit is going to change, it just means it's going to be used based on new versions of the different OpenFOAM forks. Some other things, you can find the release notes online. There's support for Precise, so the training that was meant to be on in this slot. Precise is, if you don't know what it is, it's independent of OpenFOAM, but it's a open source coupling library. So you can couple different solvers. So you could couple FE-Bio, which is a finite element software, with OpenFOAM, or you could couple OpenFOAM with OpenFOAM, or you could couple very many different, pretty much any well-known open source finite element, finite volume library. You can couple them for FSI or conjugate heat transfer. But now I worked with the guys there to make a adapter, as what they call it, for solids4foam. So now you could use the solids4foam solid solver with a standard OpenFOAM fluid solver if you wanted, or you could use it to couple a solids4foam solid solver with a solids4foam fluid solver. There's no reason to do that, but you could do that, or solids4foam with another fluid solver. And there's also some new solid solvers, vertex-centered finite volume ones that are based on the PETC linear library, new material laws, book fixes, etc. Just to show an example of with Precise, and you can find this on the website, I took the pimple over, is it over pimple diem foam they call it? It's the overset version of pimple foam from openfoam.com. So that's a fluid model which hasn't been ported yet to solids4foam. So I was able to just directly couple that with the solids4foam solid solver. So there is an example for that overset solver where you have the fluid domain in yellow, and you just have flow around a rigid cylinder. And I think the cylinder is moving in some way. But in this case, I just created a torus of deformable material, kind of rubber, inside that, so it's no longer rigid. And instead of prescribing a mesh motion on the rigid cylinder, I just prescribe it on the inside of this deformable cylinder. So I'd expect that to deform. And so just to zoom in, you can see here's the overset mesh and the background mesh. And then you can see this is the solid mesh in a different color. And you can see it's a non-conformal interface as well. So from an FSI perspective, overset's good because the FSI procedure doesn't need to know about overset because the interface is independent of the overset interface, which is just purely in the fluid solver. So if you run this case with some artificial properties, I'm moving it back and forth so you to see the little rubber donut bouncing around essentially. So this, because it was imported, this was actually using Precise to do the coupling. And this tutorial you can find on the website, you can define it in solids4foam. So at a particular snapshot of the deformation, you can see that solid is deformed and the overset region is tracking it, but then the overset interface is just like zero gradient, it's just rigidly moving basically. So if you go to the website, you'll find more tutorials. This test case is described how to run it, some details of it. And you can find down the bottom what's new in solids4foam 2.0. So it has some links and some other descriptions is here as well. Just to comment on a tentative roadmap. So at a previous conference, someone asked me, is there a roadmap for solids4foam? And I said, no, but that's a good idea. But it was more, there's an implied roadmap. So I'm an academic, I've funded projects. So typically I'm involved in projects, or other people will contribute as well, or other groups. But it's whatever's kind of funded. This is the new functionality that will end up getting merged in. So personally, and I've chatted to some people, like the v11 OpenFOAM.org v11 modular structure, since solids4foam has its independent modular structure, that means we have to just maintain everything. So it doesn't align with any of the versions. So now, since OpenFOAM v11 is introducing a modular structure, it kind of makes sense to align with their version, because in any case, it has to be ported to all the versions anyway. So that's probably the next step for v2.0 will be just to align it with that, assuming that I haven't gone through in detail that they haven't made it particularly awkward for FSI, but I don't think they have. For the solid solvers, the direction is towards coupled methods. So I have some funded projects that will start on, let's say, more coupled style approaches or even higher order methods as well. And then for FSI, I now have funded projects on monolithic methods. So hopefully by this time next year, there will be a monolithic solver. So I'll maybe talk a little bit about that later. And more benchmarking websites. But if people have suggestions, comments here at the end, you just want to suggest things you'd like, say to me, put it on the issues on the GitHub page. I'm happy to chat. Even if nobody uses solids4foam, I'm happy to work on it, and there's other people who are happy to work on it. Okay, so for the remainder of the talk, that's kind of the background. I'm going to just go through how to install solids4foam, and then I'll go through a few tutorials. Solids tutorial, a fluids one briefly, and then a couple of FSI ones, and then comment on some choices you have to make when running any of these test cases. So installing solids4foam can be done two different ways. So this is the website. If you go to the website, you can install it from source or using Docker. If you have a compatible version of OpenFOAM, installing from source should be pretty straightforward. There's just essentially 2 lines that you have to run, which we'll go through. Docker, if you're familiar with Docker, there's Docker images that are automatically built from the latest commits that you can download from Docker Hub as well. So if you go to the installation from source, you'll see how to get quickly started. There's just 2 lines. So git clone. If you want to install the v2.0 branch, you can add this option, and this will download it. For the test cases here, I'm actually going to use just the latest branch, which is called development. So development is kind of like v2.1 star, let's say. So you can just put development there if you want to download that, or you can go git checkout and change branch to development later. That'll download a directory called solids4foam, cd inside that, run the included all wmake script. And if you want, you can run the all test script, which will just check the tutorials will run. Doesn't check if the answers are right, but it just checks at least they run. So that shouldn't be quick. If you have a few cores on your laptop, it should take 5 minutes to do that, assuming you have decent internet just to download it, but it's not large. Just to comment on the versions. So the 1.0 versions were supported foam extend 4.0, 4.1, v1812, 1912, and v7. Whereas v2.0 support foam extend 4.1, 2012, and 9. So when you go to run those all wmake scripts, if you haven't sourced a version of OpenFOAM, it will complain and say you need to source a version of OpenFOAM because it's building on top. For solids4foam 3.0, I'm open to suggestions. Probably the intention is just not to support every version, but to maybe, not that there's long-term releases, but maybe every 2 or 3 years, pick a couple of versions and then just port to those. It's not that difficult to port to the other individual ones. It's just supporting all those is a real pain. You can, if you go on the GitHub, you'll find some people have even pushed or made pull requests to specific versions, and the changes are normally not drastic. Generally, except OpenFOAM.org now has radically changed the structure. If you're familiar with Docker, you can, from the solids4foam Docker page, you can go Docker pull v2.0 OpenFOAM v2012 or 9 or 4.1. You can create a container using commands like this. If you know Docker, then this will be familiar. If you want to share folders, etc., then you can start and attach to it. I'm just highlighting in green if you wanted to do it with the v2.0 version. And then if you're using, you have to source the bash at the moment. Okay, first test case. So each time I give a training like this, I try to describe a slightly different test case just to add to the documentation. So this is a benchmark proposed in this paper by Demirzic et al. It's a 3D test case meant to represent some sort of typical engineering component was the kind of idea. So there's going to be stress concentration here. So there's a hole being drilled to reduce the stress concentration. So it's fixed here. There's a symmetry plane here, and then pressure is applied, and it's steel. And yeah, that's it. Actually, this test case will be described in detail tomorrow in a talk as well, looking at a vertex-centered solver. In this case, it's a linear elastic problem. So it's essentially small strain, like a basic stress analysis type problem. This is the governing equation. I won't go in detail, but essentially this is displacement, and mu and lambda are material properties. There's a bunch of different ways you can solve this in solids4foam. So the default approach is this segregated cell-centered solver. So this is kind of like, imagine simple foam or pimple foam, except a solid version of that. But there's also a couple solver, cell-centered and vertex-centered solver, and then there's an explicit solver, there's explicit cell-centered and vertex-centered as well. There's different characteristics to each of these in terms of performance, accuracy, and types of problems you might want to solve. If you take a particular coupling in this reference paper, you can check that you get the same answers as in the benchmark test case, just to check it's working as well. And also you can look at things like order of accuracy, but I'm not going to do that here. So what does the test case look like? So I said solids4foam test cases just look like OpenFOAM test cases. So OpenFOAM test cases have, this is the test case here. You're very good. Thank you. Or grazie. So this is called narrow T member. You have a constant system and zero, but all OpenFOAM or all solids4foam test cases also have an all clean and an all run script as well. So you can check how to run the test case. What looks different? Well, in zero directory, the solid solvers typically solve for a D field, which is displacement, or DD, which stands for increment of displacement, how much the displacement changes from time to time step, or point D would be displacement at the points, if it's a vertex-centered approach. And there might be some other versions as well. In some solvers, they may solve for displacement and pressure. You might have to apply pressure boundary conditions. So if we look inside that D file, the test case as it's set up in solids4foam is using a coupled solver. So for the loading, there's a boundary condition called block solid traction, and a pressure is applied -1e⁶. So this pressure is not hydrostatic pressure. This is surface pressure. So the entire traction force per unit area is equal to whatever you give as the traction here minus the unit normal of the surface by the scalar pressure. So it's it's a surface pressure. So it's not necessarily equal to the hydrostatic pressure. This is using block solid traction. So the coupled cell-centered solver uses block solid traction, whereas the segregated or explicit cell-centered uses just solid traction, and the vertex-centered uses point solid traction. So the behavior and the functionality is the same. It's just a different implementation for the different types of solvers. So there's a different prefix for the thing. Then the fixed side, it's essentially just fixed value 0, 0, but we're using blocked fixed displacement because this coupled solver needs a special boundary condition to enforce that. And in the same way for the solid traction, you can have fixed displacement or block fixed displacement, or in the case of vertex-centered, it uses something called uniform fixed value. And then finally, the free boundaries where there's no force, like free to the air, it's just a solid traction where the stresses are just set to 0. To run this test case, which I'll do in a second, is just block mesh, solids4foam. And the only things that are different from an OpenFOAM case, a standard OpenFOAM case, are that the existence of a physics properties file. So when solids4foam first runs the solver, it looks for this physics property file, And the only thing that's in it is just, is this a solid analysis or a fluid analysis or a fluid solid interaction? And that just lets it decide if it's going to be picking a solid model or a fluid model or an FSI type model. If you set it to a solid, as we did here, then it will look for a solid properties dictionary. And in that dictionary, it specifies what type of solid solver is going to be used. If you set it to fluid properties, that's where you would set it to pimple fluid or interfluid. But then once you've set that, it'll be the same and look for all the pimple settings in the same FE solutions as a normal OpenFOAM solver. Maybe for future versions, there's a way that I can get rid of two dictionaries. And actually, the distinction between fluid and solid is maybe not important. So in V11, they actually just have everything's just a module. So maybe we'll line it with that approach. So in this case, in the solid properties, our solid model is this verbose name, coupled UNS, linear geometry, linear elastic. But that's just this particular coupled cell-centered solver. But there's also, this is a segregated solver. This is an explicit solver. So you can just change it and they might expect different settings. Let me open up my terminal now. So can you see this? Is it okay at the back? The size of the font? Okay. Okay, so this is the test case. We go 3. Oh, so much. Okay, so if I show the tree, you can see this is the structure that we're looking at. Okay, I have a folder called images. This is just how the website works, that it's displaying directly the README and images from the individual test cases. Yeah, that's about it. I can open up all run. I can see that there's block mesh and solids4foam. So create the mesh, run the solver. You can use any mesher like an OpenFOAM. You can use SnappyHex mesh, things like that. It's just quicker for this tutorial. There's a couple of scripts. You'll notice here that there's something called solids4foam scripts.sh. So this is essentially bash functions, a small number of bash functions, and primarily their functionalities to convert the case into the version of OpenFOAM you're using. So by default, all the cases are set up for foam extend, but when this case convert is run, it will look for the typically small, subtle differences, and it will replace those or make those changes in the test case. So like symmetry plain maybe becomes symmetry, or maybe some dictionaries might be lists in one version. So it just goes through and makes those changes specific for solids4foam. So this won't work in general for any OpenFOAM solver. And sometimes I'll have a function. In this case, some of this, the choices will only work with one version of OpenFOAM. So in this case, this particular block coupled solver only works with foam extend. So this will just quit with a kind of silent warning that you can't run this if you're using a different version. Okay, so I'm using foam extend 4.1 for this block mesh. Let me open up this test case actually, just so you can see it. Oils, solids, linear elastic, an RLT member. View. Okay, so you can see this test case made in block mesh. We're just looking at, and you can see the mesh is graded towards the hole. Okay, so then I'm going to run this solids4foam. It's going to start solving this. So it assembles the equation. This is using the foam extend block solver. This way, this particular couple solver only works in foam extend. So for this particular one, and this is one reason that some of the other solvers were moving towards using PET-C, but the block couple solver struggles to solve some of these. So this looks like it's not going to converge 1E22, but it actually converges. It'll go down to 1E-6, and it seems insane. But if there was a better preconditioner, it will converge much better. We've noticed using PET-C, but in this case, this is fine. I know it will converge. So I'll let that run. It only takes maybe another minute, but I'll just go through these slides while I'm waiting for it to run. One short comment on something called geometrically linear or geometrically nonlinear approaches in solid solvers. This applies just to solid mechanics in general. The default analysis type, like if you're using SolidWorks and you do stress analysis, will be linear geometry, and that's also known as small strain approach. So it'll assume the deformation is small, and if that's true, you can simplify the governing equations, and they're easier to solve, and you can even make them linear if it's linear elastic. But in general, solid mechanics equations are nonlinear. Even if it's elastic, they're nonlinear, because when you apply a small force, the geometry changes. So if you're integrating over a cell, the area is a function of displacement. So if your stress is a function of displacement and the area is a function of displacement, even if the stress is a linear function, the whole thing's nonlinear. So that's what geometrically nonlinear approaches are. So they're called large strain approaches or finite strain approaches as well. They're always correct. They'll always give you the correct mathematical answer, but they're often slower and less stable. So if you run both of them, you get a different answer. You need a nonlinear approach. But typically linear approaches are okay for lots of problems. So while that's still running, there's, instead of transport properties, there's something called mechanical properties. That's where you define your material model. So in this case, this name steel doesn't mean anything unless you have multiple materials. If you have multiple materials, then steel, it'll look for a cell zone called steel and a cell zone called aluminium. And then that's how it knows which is steel and which is aluminium. It's based on cell zones in your mesh. But if there's only one material that's steel, the name's not used for anything. So in this case, linear elastic, to give density, Young's modulus, Poisson's ratio, but there's a bunch of other material laws you can use as well, like elasticity, viscoelasticity, thermoelasticity, poroelasticity, lots of ticities. And also there's gravity. You can turn on gravity if you wanted to. Okay, it's still going. You can see they're not 1 to 22 anymore. They're converging. In this case, it's just it's very erratic convergence for this particular case using this particular solver. Okay, it's not done yet. Okay, we're almost there. I realized today while traveling, I didn't actually have foam extend for 4.1 on this computer, so I'm connecting to a server in the office. Solids, linear elastic, narrow. Okay, converged. So just to view this, I'm going to copy the results across my local computer. Bear with me. This thing out of the way. Okay, so just one time step. Let me refresh. This thing out of the way. Oh my God. Okay, I'll leave it there. Okay, so if I look at the different fields I have the displacement field, which is a vector. I have velocity field. Epsilon is a strain tensor, so that has 6 components. Sigma is the stress tensor. And then I have something called epsilon equivalent and sigma equivalent. So the equivalent stress is also known as the von Mises stress as well. Kind of like a von Mises strain. So it's a scalar. And you've got hydrostatic stress, which is the negative of pressure. So typically in these solid type analysis, you may want to see the kind of what the deformation looks like. So we'll use this filter here in PowerView called warp by vector. So that lets us move the mesh by the displacement field. So if I press apply, nothing really happened because the displacements are tiny. It's a steel component that has a relatively low stress. If I just rescale this up to a large number, then you'll see this is the deformation multiplied by 40 to the 4. But you can see the kind of type of deformation, even though it's very, very small. So you can see it's moving down like this. And remember, in this case, it's a symmetric case. So you can view the full geometry as you would in a fluid analysis just by using the reflect filter. It's actually symmetric on the back as well, but yeah, you get the idea. So you can see it deforming. You can see the displacement field just kind of bends down. You look at the von Mises stress, the equivalent stress. So this is normally, if you're designing a component, you want to check the von Mises or the equivalent stresses below the yield stress of the material. So if it's above it, then it's going to yield. So in this case, it's 16 megapascals. Steels are normally in the orders of hundreds of megapascals or even higher in some cases. So this will probably be fine. So you can see you get a stress concentration, and it makes sense. But this is maybe why you drill a big hole. If you have a very sharp corner there, then you might actually get locally yielding. You can also look at all the different other components of the stress tensor, the XX, YY, etc. So, okay. So just to point out, that's a linear geometry, a small strain approach. So since it assumes the deformation is very small, it doesn't move the mesh. So if you want to see what the deformation looks like, you actually have to warp the geometry by the displacement field. So if you wanted to change things around, I'll keep going, but you could easily try a different solid solver or change the loading, change the material, add inertial effects. Actually, yeah, okay. If I had time at the end, I can come back to that. Okay, I'll keep this part brief. So you're not going to use solids4foam for doing a fluid analysis in default, but since we have to do FSI, you can actually do a pure fluid analysis in solids4foam as well if you wanted. So why would you do this? Well, if I port a new fluid solver, I might want to benchmark it and check it gives the same answer. So there's only one tutorial called Cylinder and Channel. It's described on the website as well. So this is a kind of standard CFD benchmark you're probably familiar with. So it's a channel with a rigid cylinder flow over it, and different Reynolds numbers gives different behaviors. You can get von Karman vortex streets, etc. So for example, in Furtzer and Perich, the CFD book, they describe this test case, a 2D and 3D version. So how is a fluid test case different from a normal OpenFOAM fluid solver? Well, you have to have a physics properties, which just says type fluid. And then it will look for something called a fluid properties, and that will just say pimple fluid. So if you run it in this case, it's pretty quick to run. It's set up with, I think it's a Reynolds number of 100 based on the cylinder diameter, and that will give nice laminar vortex shedding von Karman vortex street. So I can check. I use OpenFOAM 2012, solids4foam tutorials, fluids. There's only one test case. Oh, I have the results stored, one I made earlier. So if I go all run, you'll see that the first thing it does is it converts the case. So you'll see here are the changes that actually made to make it compatible with OpenFOAM v2.0. So RAS model is changed to RAS in turbulent properties. Time-varying uniform value is called uniform value. And there's some change, the change dict is defined, dictionary is defined differently as well. So then it runs fluent mesh to foam. This mesh is stored in the fluent mesh format. Then change dictionaries run. Then the solids4foam solver is run. I might just stop that and just run it so you can see what it looks like. So this should just look like pimple foam, except it has this one line saying evolving fluid model pimple fluid. So I'll open up another terminal. Oh, fizzy water. Oh. Sorry. Yeah, you don't have any lots for you. I'll use the paper for now. It's not on any computers. Yeah. Okay. So 2D test case. This is what the mesh looks like. I think Jelko Chukovitz made this mesh, I think in Gambit. So if I skip and I refresh, get some more time steps, then you can play it. It's pretty quick to run. So you'll see the vortices forming and then they start shedding at a certain point. So you can run this with pimple foam and check the answers are okay. So it's curious as well because the port, yeah, thanks, sorry about that. If you run the 3 different versions supported, there are 3 different ports of pimple foam. So actually the foam extend 4.1 version of pimple foam is a little bit less stable for some reason, but you get slightly different answers with each of them. Okay, FSI test case. So I have a couple to look at, flexible dam break, and then the 3D tube I'm going to look at. Okay, so you saw this one at the start. The geometry is just the dam break tutorial. And then I just add a little simple block mesh for the block itself. We've water, air, and then we've kind of like a rubber, because if it was steel, it wouldn't move at all, really. Gravity, the bottom edge of the dam is set to 0 displacement, and then you have an FSI interface. Gravity won't really make much of a difference. I think gravity's turned on in solid, but it's like minuscule, the deformation. It causes it to sag a little bit, but it's very small. Just to comment on the governing equations. I have a question here. Extends, what kind? Okay, I'll go through those Q&A at the end. So the fluid, this is the interfoam or interdiem foam. So Navier-Stokes equations on the volume of fluid, conservation of this alpha field. Solid solver is just a dynamic version of linear elastic in this test case, even though it could be a nonlinear version. And then we have these extra FSI interface conditions. So the way it works in solids4foam, it uses what's called partition coupling. So it solves the fluid, then the solid, then the fluid, then the solid, and it passes information between them, as opposed to monolithic, where it creates one giant linear system and solves them all as one material. So the partition approaches have to try and force kinematic constraints and kinetic constraints. So kinematic, the velocity of the fluid and the solid at the interface have to be the same. Otherwise, there'll be a gap between them. And that implies the displacement must be the same as well. So that's the kinematic, that's on the motion. Then kinetic, it just means that the forces have to be equal and opposite, essentially. So within each time step, depending on the coupling approach, it will iterate to try and force those to some tolerance. So that's the two approaches, this partition approach in solids4foam, and then monolithic, hopefully in OpenFOAM Workshop 19, there'll be a monolithic solver. But I'm sure there's other people even working on this area as well. Maybe keep that for a little. Just a note on parallelization. The way it's implemented at the moment, solids4foam, is we use a global polypatch. So the entire interface is reconstructed on every processor. So that's maybe fine for tens, maybe up to hundreds of cores, but then it'll probably is not the most efficient once you get to hundreds of cores. That's actually, Precise does it a different way. That may scale better, but that can change. Okay, so what does the test case look like? So the way the FSI is implemented, it takes advantage of OpenFOAM regions. So immediately you should see over here in the 0 directory, we have a fluid and solid subdirectory. In the constant, we have a fluid and solid subdirectory, and in system, we fluid solid. So essentially, it's just two cases on top of each other, except the fluid 0 is just inside 0 fluid, and the solid 0 directory is inside 0 solid, and the same for constant system. So that's essentially the only difference. But once again, when solids4foam runs, it will look for physics properties. That's the first thing it looks for. This time it's set to FSI, or fluid solid interaction. Then it'll look for FSI properties in this top level. So that defines the coupling approach, like this Atkins or IQNILS method. And then it will expect these subdirectories. So for example, in the boundary conditions, you have 0 fluid. This is the dam break. So it's interdiem foam. It's the diem, the dynamic mesh version, because now the mesh is moving, not like in a normal dam break. The mesh moves because of the solid. So you have to have an ALE formulation. So velocity, dynamic pressure, the alpha field, but now you have a point motion because you have a mesh motion solver. And then displacement in the solid. In the constant, you have your fluid properties, transfer properties, etc. Dynamic mesh. In the solid, you have solid, just like we saw previously, and the same for the system. If you look at the all run in this case, you just go block mesh dash region solid. So most of the OpenFOAM utilities have a region option, which means look for a region with this name and then run and create the mesh or do whatever in that region, like set fields. So you can go block mesh dash region solid, block mesh dash region fluid to make the two independent meshes, then set fields dash region fluid to set the initial dam, and then you can just run solids4foam. I'll try to do that now. So I'll use OpenFOAM 2012. Should work for all of them. So tutorials, you'll see we've solids, fluids, fluid, solid interaction, and the precise tutorials are kept separately. Fluid, solid interaction. So we have flexible dam break, and then I kept the results as well. We'll run all run. So you can see it converted the case. There's some extra options. Symmetry planes are renamed in the block mesh and boundary. I'll just stop it on the solids4foam solver. So it should just look like interfoam running, but then you should see is solid running as well. So this part goes to this time, and then it solves inter-diam foam. So it's solving the mesh motion first, then alpha field, velocity, momentum predictor, and then pressure correctors. And then it takes the forces and it interpolates, and in this case is using AMI to interpolate the forces onto the solid. You can see it prints out the current forces on the interfaces. Then it passes out the solid, solves the solid a little bit. Then it takes a motion of the solid and passes the motion back to the fluid to update fluid mesh. And that's one iteration in the time step. So you can see it's done 7 FSI iterations in the time step. So it has to solve fluid solid multiple times. So FSI tends to be much slower than a pure CFD simulation, for example. Okay, so that's running. Let me open another terminal. So if I look in PowerView, you'll see PowerView automatically recognizes the 2 regions. So PowerView will look for subdirectories inside constant. And if it finds a polymesh folder in any of those, then it assumes it's a region. So it doesn't know the names of regions. It just looks for a polymesh folder in a subfolder. So you can see fluid and solid. So there's different ways to load it, but you can see PowerView sees that there's 2 different regions and it even colors them differently. And in this case, yeah, it's a non-conformal interface as well. So sometimes it's useful to display different fields in the different fluid or the solid. So you can either load the case.foam twice, or you can use something called extract block. So if you search for extract block, so extract block lets you take out the fluid as its own part. So this is going to be our fluid. And if I click here and I go extract block solid. Extract block is actually useful if you just have a fluid case. If you just turn on all the patches, then you could extract out just the internal mesh and then separately have a patch. You could color a patch different from the internal mesh. So it's handy. So now I have a fluid and a solid. So if I turn on the mesh in the solid and turn on the alpha 1 field in the fluid, and then if I just refresh it because it's still running, get this thing out of the way, press play. And it's not alpha 1. I'm going to show alpha, I guess. Oh, alpha.water. Okay, so the first thing you'll notice is the fluid mesh deforms correctly, but the solid just stays still. So this is a small strain solid solver, small strain linear geometry. It assumes the deformation is small. It doesn't move it. It solves for the true displacement. It just doesn't move the mesh. So the deformation of the interface is the true deformation. That's what the fluid solver sees, but the solid solver doesn't actually move its own mesh. So once again, we can just go warp by installation field, and then we'll see the actual deformed solid geometry. Good. So we can look at things like the von Mises stress. So classic bending, it will be at the outside. The high stress is at the outside. So particularly at the fixed region. So you get a high stress at the bottom. So if we change this to a plasticity model, then you might expect plasticity in those regions. So if we look at the maximum stress, okay, it's very, very small, 33 kilopascals. Okay. Fine. Okay, we'll keep going. Okay, so another FSI test case. 3D tube. So this 3D tube test case is described on the website as well. Okay, water stop moving. So this is kind of a classic FSI benchmark. So it's sometimes called a water hammer test case. So you have a tube, a pipe. So it's actually a 2D problem. It's axisymmetric, but in this case, we set it up as a 3D problem. But it is actually 2D. So you have a deformable pipe, and then you have a typically assumed an incompressible fluid. So you have zero pressure at the outlet of fluid, and then you apply a kind of step function of pressure. So you just suddenly apply a high pressure, and then you hold it for a time, and then you drop it. So like a step pressure. So if it was just rigid walls, the pressure wave would travel infinitely fast in an incompressible fluid. So you don't see a wave of pressure traveling. But you have this interaction when you have a deformable, flexible wall that there's a finite wave speed in a compressible solid. And that actually creates a finite wave traveling in the fluid, which is kind of interesting. So this is often used because there's, I think there's an analytical solution as well for it. So you can monitor the displacement of a point on the inside of the pipe halfway down, and you can look how it moves, and you can change numerical settings and try to understand how it's affected by it. So you can find more details of this test case and papers describing it in detail as well on the website. So if we look at that point A, the sort of results we might get, I know you probably can't read this, but this says radial displacement. So on the diagram there, it's like vertical displacement. So outward displacement of point A in time. So as the wave passes it. And what are all the different graphs? This is the effective time step. So we're using a first order time scheme, Euler first order time scheme for the fluid and the solid. And it just shows that the big squares means big time step, the little squares means little time step. So if you have a large time step, you'll see that it moves out and then it moves back in and then it kind of goes back again. But as you keep reducing the time step, the peak keeps increasing. So it is converging, but if you notice here, this is characteristic of first order convergence. So half the time step, the error halves essentially. So it's not like second order. So it's quite slow to converge. So you probably need to refine it even more to get to a time step converged answer. But if you run it with second order scheme, so backward, which is second order for the fluid solver and for the solid solver, then you'll have here's the same large time step, but you can see as you refine it, then the last three time steps are almost converged. So if I just flick back between those two, you can see that even the middle time step is almost better using second order schemes rather than the finest. So I just put them all together. You can see this is the finest for the first order scheme, but you can see the three finest time steps are better for a second order scheme. That was a kind of a by the way. But just the reason I'm pointing that out is if you have a second order time scheme for your fluid solver and first order for the solid, then your overall method will be first order in time. It just is the lowest common denominator. Whichever is the worst, that's what everything will be. So it's just an extra, not problem, challenge in academic proposal writing speech. It's an extra challenge to be resolved. So just to comment on FSI coupling in solids4foam, there are two classes approaches currently in partitioned FSI in solids4foam. There's Dirichlet-Neumann coupling, which is kind of the standard partition approach, and there's Robin-Neumann coupling. So Dirichlet-Neumann is a kind of black box approach, and precise methods are based on this. So you don't need to change your fluid solver or solid solver. You're just passing information between them. So you could use it with a commercial solver and just update the boundary conditions. This type of approach. Whereas Robin-Neumann is an intrusive approach. You actually have to hack the pimple algorithm in certain places to get it to work with this. So Dirichlet-Neumann, essentially the solid is a Neumann condition and the fluid is a Dirichlet condition. So you're kind of passing from one side. That's why it's called. So for either of those approaches, you can try accelerate the convergence as you're passing information. So you can just use fixed under relaxation to promote convergence, but you can use a dynamic relaxation, Aitken's method, or you can use this IQ NILS from De Groot et al., which is a kind of state-of-the-art method, kind of quasi-Newton method for convergence. So this is the default and precise is this method. And then separately in the literature in FSI, incompressible fluids, if you just make them weakly compressible, a little bit compressible, it makes it easier for the FSI method to converge. So when it's like for example, if you're filling up a balloon, then having a fully incompressible solver, then a slight error in the interface just destroys the continuity and you can't converge the thing. So you need special methods, but weakly compressible fluid solver will help you in those cases. So you can also try that with each of those methods. So for this 3D tube test case, you can do at least 6, but you can actually do more in solids4foam, but just to keep it manageable, we can try Dirichlet-Neumann using Atkins and an incompressible fluid, or IQNLS and incompressible, or we can do the same with weakly compressible. You can also use the Robin-Neumann approach with Atkins and incompressible, but you could do it with weakly compressible and the other approaches. And then just for comparison, I ran the test case using Precise, which uses a form of IQ and ILS with incompressible fluid in this case as well. So the first thing was I just, for a given time step, and in this case, a large time step using the Euler first order method, I just ran all of them to see if I get the same answer. So essentially you get the same answer. The greatest difference is the green ones. So the two green ones are the weakly compressible. So essentially you have like a compressibility. And if you set the compressibility to 0, you get the same answer, but then it's not weakly compressible. So the more compressible you make it, the more different the answers are, but maybe the better to converge. So it's kind of like it's a penalty factor that you can choose how much improvement in speed you want and how much loss in accuracy. This plot, which is messy, shows the number of FSI iterations per time step across the entire simulation. So if I just take this red one, it's taking about 50 fluid solid iterations per time step. So because the first time step, and it solids the fluid and solid, and then does that 50 times. So it'll be 50 times slower than just a pure CFD simulation. So these two slowest ones in this case, we have the Dirichlet-Neumann-Atkins approach in solids4foam, and then the blue is the Robin approach. In this case, the Robin approach doesn't work very well with the current settings. The best ones, we can see green dashed, which is weakly compressible IQN-ILS, red dash, which is Dirichlet-Neumann IQN-ILS, and then orange is precise using IQ-ILS. So it's just all the quasi-Newton approaches essentially give very similar behavior. This is not a perfectly fair comparison with precise because it defines tolerances differently. So I wouldn't worry about it too much because it may be converging tighter or looser, but broadly it gives the same behavior. And then the weakly compressible Atkins is somewhere in between. So generally weakly compressible is better and IQN-ILS is better in this case. I then changed to a much smaller time step. Yeah, I think this is still first order though. Get the same answer. And then for this much smaller time step, the behavior is kind of similar. So once again, Dirichlet-Neumann. Where's my mouse? Don't know. Okay. Oh, the screen is frozen. Okay. So the top one here is Dirichlet-Neumann-Atkins, which still is actually taking more iterations. Even though the time step's smaller, it's actually taking like 60 iterations. But the IQ-INLS, so precise and solids4foam are taking similar, maybe 12, 13, 14, 15 iterations. The weakly compressible solvers are both better. Now the time set's smaller, so they're both giving lower numbers of iterations. And in this case, once the time set's small enough, the Robin approach is really efficient. So if you have a very small time step, the Robin approach, in this case, takes exactly 5 for every time step. So it really rapidly converges. So the Robin approach, the way it works, that some assumptions it makes only make sense for small time steps. So in this case, this smaller time step ran faster than the larger time step because the larger time step was taking 50 iterations. This was only taking 5. So a smaller time step can actually make your overall solver faster in FSI. So let me just see if I run it. This test case is a bit slower. I use solids4foam. This I'm using 2012 here just because I have installed tutorials. Fluid solid interaction, 3D tube. So you can see there's all run pimple fluid by default, but there's sonic liquid fluid. So sonic liquid is a weakly compressible fluid solver. So I'd use this barotropic equation just to make it a little bit compressible. So if I run this, monitor the log. So it's a bit slower here because the solid solver, the segregated solid solver is a bit slower in this test case to converge. So I can open it in power view, but I don't think we're going to get anything interesting to see for another probably 10 minutes or something like that. Okay, so this is the test case. So it's 3D. We're using symmetry planes. I can extract blocks again, so I can extract my fluid. I can extract my solid. And then it's a small strain approach here, so I can warp the solid as well. So if I refresh, I don't even know if we have any time steps here. No, okay. So there's nothing to show at the moment. But okay, if you run it, it will run through and you can check the different results. Also, all the results from the web page, if you go to the website, there's a separate repository on the solids4foam GitHub page, which just, it's a repository if you want to download the raw results for all the different approaches in the case set up in different ways, if you want as well. That is it. Just a comment. I got lots of acknowledgements in different funding bodies. I was fortunate to get a European project which will start next year, and I'll be looking for postdocs and PhDs, and they're going to work in FSI and solids4foam. So if this is something that you're interested in and you want to come to sunny Dublin, where it never rains, then come have a chat with me. Cool. Thanks very much. And if you have any questions, just shout them out, and in the chat, you can just put them in online. So just to answer live the question in the chat, does solids4foam include all of the solid mechanics functionality of the foam extend, or is it a subset? What kind of solid physics are available? So yes, it should. So the solid mechanics folder or directory in foam extend is something that I created and pushed. So solids4foam is an evolution of that. So all of that has been refactored into a single executable form, and extra functionalities have been added. So I'm almost certain at least 95% is there. There might be some particular functionalities which have not been used since and maybe have not been ported, but almost all of it should be there. And if you find something not, you can just put it as an issue. Any other questions? Yeah. Yeah. Yeah, so I think you kind of answered I think you know the answer to, or you answered the question. So yeah, you're correct. You need a shell formulation. So there is, which is more of a proof of concept. If you open, you go to tutorials, solids, there's a folder called beams, plates, shells. And it has this clamp plate, and it's using the finite area method, and it implements plate equations for finite area. But that would need to be extended to a general shell. And to be honest, that's more of a proof of concept than a true shell solver. So you need a true shell solver. So there is, it's same for beams, but there is actually a beam solver. So there's a talk, Zhalko Tukovic and Shivani Bali, it's a PhD student coming to them. They've worked on a beam solver, finite volume based in OpenFOAM beam solver, which is a true geometric beam, non-linear geometric beam. So if you need a beam, that doesn't help you for an airfoil, but essentially it just, yes, it can be done. It's just nobody's done it. So yes, doing a 3D approach wouldn't be efficient probably. Yeah. No problem. Yeah. So you can definitely do precise. Definitely, that's one of the main things they look at in precise. So there is, if you go back here, the physics, the tutorials are broken down kind of by physics. So there is thermoelastic. So there's this hot sphere test case, which is described on the website. So it's actually the first tutorial is a thermoelastic pressure vessel. So it's you have thermal conditions, stress conditions, you have like it deforms. There's a reference solution in this case that's kind of interesting. So that works, but the FSI part, there is a branch, maybe a stale pull request, that somebody did port it to use thermal coupling to couple the interface, but I'm not sure the status of that. It wasn't integrated because there was a lot of changes. So you could definitely do them precise. So you could use this solids4foam solver, pick thermoelastic solid model, thermoelastic mechanical law, and then couple it with precise. I think that should work. Yeah, it would actually be nice. It's a good idea actually to add a tutorial on that. Maybe that's something we should do. Yep. This is for the quasi-Newton, the IQN. So I'm pretty sure the implementation, which I didn't write, may have been Joris de Groote's implementation in foam extend, his old version anyway. And then I think Jelko Tukovic, then that went into extend bazaar, and then that was taken and put into this. So yeah, that has a reuse flag, which sets the number of previous interface fields to try guess the new field. Yeah, so that yeah, it's there. That's a good question. I don't know. I can't remember. Yeah, it'll change the behavior. So set to 2 in this case. So yeah, I think it definitely does. It's definitely better. If you set it 0, it doesn't work as well in this case. Okay, that'd be a problem. Okay. Right. Okay, if there's nothing else, then yeah, feel free to come down and chat to me afterwards or see me around. And yeah, thanks for coming.